If you've ever driven alongside a heavy truck and noticed a full set of wheels suspended in midair, you're not alone. It's a detail that's easy to overlook until you realize those wheels are spinning with the rest of the rig, yet never touch the road. What looks strange at first glance is actually a precise piece of engineering, adapting to the road in real time, saving money, protecting infrastructure, and solving problems most people never knew existed. The secret lies in understanding a fundamental truth about heavy trucks. It's not how much they weigh that matters most. It's how they distribute that weight. And that distinction has shaped an entire industry. Think about walking across fresh snow. Wear regular shoes, and you'll sink straight through to your ankles. Strap on a pair of snowshoes, and suddenly you're gliding across the surface like it's solid ground. The difference isn't your weight, it's how that weight gets spread out. Roads work the same way, except instead of snow, we're talking about asphalt and concrete that cost millions of dollars per mile to build and maintain. In the US, federal law caps most trucks on the interstate highway system at 80,000 pounds gross vehicle weight, though states often allow more under special permits. But that number alone doesn't tell the whole story. What really matters to road engineers is axle loading, how much weight each individual axle presses down on a specific point of pavement. In practice, that 80,000 pounds is often distributed as about 12,000 pounds on the steering axle and about 34,000 on each tandem set, keeping the truck within typical federal limits. Concentrate more weight on fewer axles, and suddenly you're exceeding legal limits and creating dangerous pressure points that can crack pavement, buckle it, and turn smooth highways into expensive repair projects. The mathematics of road damage are particularly brutal. Engineers have discovered that road wear increases exponentially with axle weight, following what's known as the fourth power law. Double the axle load, and you don't just double the damage, you increase it by a factor of 16. This means a single overloaded axle can cause as much road damage as thousands of properly loaded ones. Highway departments have learned this lesson the hard way, watching expensive pavement investments crumble under the assault of concentrated weight. This is exactly where lift axles come into play. They add extra weight-bearing points when dropped, spreading the load to stay legal. When the truck is empty or lightly loaded, those extra wheels lift up and out of the way. When it's carrying a full load, they drop down to share the burden. But the engineering goes deeper than just protecting roads. The US government has turned axle weight limits into serious business, with fines that can reach thousands of dollars for a single violation. Some states operate sophisticated weigh-in-motion systems that can measure axle loads while trucks are traveling at highway speeds. Get caught with too much weight on too few axles, and you're facing steep fines, possible out-of-service orders, and being forced off restricted routes until you're legal. The enforcement technology has become remarkably sophisticated. Many modern systems use sensors in the roadway to check axle weights at highway or near highway speeds, then route suspect trucks to a weigh station for a closer look. These systems record axle weights, spacing, and sometimes vehicle classification, but they don't measure tire pressure or mechanical faults. There's no hiding from this level of scrutiny when it comes to weight distribution. New drivers sometimes learn this lesson the hard way, approaching a weigh station without realizing their axle configuration puts them over the limit. Experienced drivers, on the other hand, anticipate these checkpoints. They deploy their lift axles well in advance, ensuring that their weight is properly distributed long before reaching the scale. What might seem like a last-minute move is actually a routine part of responsible load management. The lift axle turns complex weight management into a simple switch flip. As a truck approaches a weigh station with a heavy load, the driver can deploy those floating wheels in seconds, converting the truck from a 5-axle configuration to a 6 or 7-axle setup. The total weight stays the same, but now it's distributed across more contact points, bringing each individual axle within legal limits. It's not a loophole, it's built-in compliance through smart engineering. It's pneumatic engineering. The driver flips a switch, the valves send air to lift bags that raise the axle, usually 90 to 120 psi, or vent them so the suspension drops it to the pavement. Each axle is often rated to carry loads approaching federal single-axle limits, depending on configuration, but not all lift axles are created equally. Tag axles mount behind the drive tandems, pusher axles sit ahead of them, and some even feature self-steering capabilities to reduce tire scrub during turns. Each configuration serves different truck designs and load requirements, from highway tractors to specialized heavy haulers. More sophisticated systems don't even require driver input. Automatic lift axle systems sense suspension pressure and reactively deploy when load thresholds are reached. These systems use pressure sensors in the main suspension to determine when the truck is approaching its axle weight limits, then deploy the lift axle when needed. The economics of lift axles extend far beyond avoiding fines. Lifting unnecessary axles cuts rolling resistance for instant MPG gains, extends tire life, and can save fleets hundreds of gallons of diesel yearly, hundreds of dollars per truck. When a lift axle is deployed unnecessarily, those tires are accumulating miles and wear without providing any benefit. Worse, they're often running at reduced load, which can cause irregular wear patterns that shorten tire life even further. Then there's the toll factor. Many major toll roads, including several in the Northeast and Midwest, charge trucks based partly on axle count, with each additional axle adding dollars to the toll bill. A truck with its lift axles deployed might pay significantly more in tolls than the same truck with those axles retracted. On routes with frequent toll plazas, the savings from lifting unnecessary axles can offset the cost of the entire system within months. But perhaps the most ingenious aspect of lift axles becomes apparent when these massive trucks need to navigate tight spaces. Picture a heavy truck trying to make a sharp turn in an urban area. With all axles locked in position, the truck becomes a rigid, unwieldy beast that fights every attempt to change direction. The rear tires don't follow the same path as the front wheels. They cut across the inside of the turn, scrubbing sideways against the pavement in a phenomenon engineers call tire scrub. This scrubbing action is destructive on multiple levels. It tears chunks of rubber off the tires, leaving black marks on the road and shortening tire life dramatically. It puts enormous stress on the suspension components, wearing out bushings, joints, and mounting hardware. While tire scrub accelerates tire wear and scuffs pavement surfaces, most structural road damage still comes from vertical load cycles, but the lateral forces certainly don't help road longevity. The physics of tire scrub are particularly harsh on the equipment. When a tire is forced to slide sideways while supporting thousands of pounds of weight, the friction generates enormous heat that can literally cook the rubber compounds. This thermal damage weakens the tire structure and can contribute to sudden failures later on, which are especially dangerous if they happen at highway speeds. The lateral forces also accelerate wear on wheel bearings and suspension components. Lift axles solve this problem by allowing trucks to temporarily shorten their effective wheelbase. With one or more rear axles lifted, the truck becomes more maneuverable, able to follow tighter turning radii without the geometric constraints of too many fixed contact points. It's like the difference between trying to push a long, rigid pole around a corner versus maneuvering a shorter, more flexible stick. The truck effectively reshapes its footprint to match the demands of its environment. Modern lift axle systems have evolved into sophisticated technologies that would seem like science fiction to truckers from just a generation ago. Some advanced suspension systems can interface electronically with other vehicle systems, but most lift axles still operate through standalone pneumatic controls. On some advanced systems, electronic controls can adjust how much weight the lift axle carries to help balance traction, wear, and maneuverability in different situations. The technology continues advancing toward greater automation and intelligence. Engineers are experimenting with GPS-assisted systems that could, in theory, drop extra axles before a weigh station or retract them on curvy sections to improve handling, but most trucks today still rely on load sensors or driver input. The concept involves using route information to anticipate when axles will be needed, but this level of predictive control remains largely experimental. The sophistication extends to specialized applications where lift axles serve unique purposes. Many concrete mixer trucks use lift axles to meet weight restrictions when traveling empty to job sites, improving fuel economy and staying legal. But when they load up with wet concrete, those lift axles drop to distribute the massive weight shift as the liquid load sloshes around during transport. Many garbage trucks lift rear axles when empty to improve fuel economy and maneuverability in residential neighborhoods, then drop them when fully loaded. Heavy haul trailers often have multiple lift axles that can be deployed as needed as load increases, creating a graduated response to changing weight distribution needs. The maintenance aspects of lift axles reveal another layer of complexity that fleet managers must navigate. Unlike fixed axles that see constant use, lift axles face the unique challenge of intermittent operation. Seals and gaskets can dry out and crack when axles remain lifted for extended periods, while brake components may sit cold and unused for thousands of miles before suddenly being called into emergency service. This creates unusual wear patterns that require specialized maintenance schedules, balancing the benefits of reduced road contact against the potential problems of sporadic use. This level of automation represents a fundamental shift in how we think about commercial vehicles. These aren't just trucks anymore, they're adaptive machines that reshape themselves based on load, route, regulations, and driving conditions. The floating tires you see on the highway are just the visible manifestation of a complex system that's constantly working to optimize performance, reduce costs, and minimize environmental impact.